This program was brought to you by Koller Institute of Venture at Tel Aviv University.
Okay, I'm going to talk now about my own research, so I may do it better than before. So my main activity in the group in the last 5 years is related to nanowires and a new paradigm in nanowires. So since I'm limited in time, I'll try to do it fast. So what are nanowires good for? First of all, what are nanowires? Nanowires are tiny wires, few nanometers or few tens of nanometers in diameter. They're good for energy, good for electronics, good for sensing, but we're going to focus today on sensing and electronics. There are two main ways to fabricate nanowires. What is called the top-down approach. This is what Intel is doing, taking a big piece of semiconductors and sculpture it down to a very thin channel on nanowire, 22 nanometers in size. Actually, the new fab in Kiryat Gat is going to be a 10 nanometer based transistor, so this is a huge achievement. Another approach is the bottom up, to grow the nanowires like mushrooms. And this is done chemically in a process called chemical vapor deposition. This is very popular in the scientific community, but the problem is that to fabricate devices out of these forests of nanowires, never going to do it to make it to the market. This is my opinion, because you have to take these forests and fabricate the transistors almost one by one. So we have developed in the last 3 years a new paradigm, and this is not the bottom up and not the top down, and we call it electrostatically formed nanowires. In essence, what you have to remember from this talk, that we shape the nanowires electrostatically after a transistor is fabricated. And I'll try to explain it very, very briefly, not to go deep into science. So the conventional way is to fabricate the bottom-up nanowire into a device, and this is never, to my opinion, never going to make it to a huge market. What we are doing is taking a regular transistor and take the flow of carriers and shrink them electrostatically to a 5 nanometer cylinder or to a 5 nanometer nanowire. And this is a kind of a revolution in the field. Sorry for being a little bit overstating it, but it's a kind of a revolution. So we cannot compete with Intel, because this is as Adi said, this is a $5 billion fab or even more. So we're not going to compete with them. And what we are doing, don't go into the details. We take a transistor and electrostatically, by different applied voltages and gates, we shrink the carriers to a very, very small cylinder, even less than 5 nanometer, that we've demonstrated recently. This is a top view that you can see that we actually make it. And without going into the details, and I'll discuss it over lunch with our group, you can see the nanowire here, pictorial, very in a cartoon. We can also move the wire, since it is shaped electrostatically by applying different bias on the gates of the transistors. We can move the wire or move the nanowire, and this is the basic for the main application, which is a new kind of a transistor. I cannot share with you all the details of the transistors because it has only been submitted now for patent, but this new kind of transistors can make the logical circuits much simpler than what we think is current technology. And this is related to what the industry is looking for, which is called beyond CMOS. CMOS is the name of the current microelectronic technology, and the industry is looking for solution beyond CMOS, because in a few years you cannot do the transistor smaller than about 5 nanometers, will probably be the limit. And then the industry and the community is looking for other solutions or new paradigms. And this is, we think that our approach is maybe one of them. So I'm not going to go into technical details. I'll just give you the bottom line. Instead of doing a multiplexers with 40 transistors in the current technology, and you don't have to understand what a multiplexer is. Do a certain logic operations with 40 transistors. We believe that in the new approach, we can do it with 6 transistors. So in short, we can reduce the number of devices by an order of magnitude. So one of the advantages of our new device that one of the variants of the device can do ternary logic instead of binary logic. Binary logic is 0 and 1. Our device in certain formats can do ternary logic. This is 0, 1, and 2, and it can make numerical calculations and logics even more efficient. And I didn't talk about it because I cannot, as I've said, the details are in the patent, but this new logic is one of the reasons why we can reduce the number of devices sometimes by an order of magnitude. And surely if we approach circuit designers or more expert people from the industry, we may even think of new applications or new logic elements. We're just in the beginning, and as I said, our expertise is not in the logic. Our expertise is in the device itself, designing the transistor itself, and I'm sure we can benefit with interactions with experts in the field. The problem is how to do it without revealing all our secrets and selling out it very cheaply. What are the next steps? And I think this is my aim in this afternoon, to gain some experience, to learn something from the people here. The required funding that I hope to discuss this afternoon, we are thinking whether to apply, for example, whether to apply for funding now or whether to approach VCs. Of course, one of the main obstacles is it's not on the market yet. Don't be so excited. We have to prove that our new approach or our new paradigm has lower power consumption and a similar speed of operation as conventional transistors. If it is not, it will not be a big thing. But in order to do so, or in order to demonstrate it, we need some funding and we need some time, and these issues will be discussed in the roundtables this afternoon. So for example, several questions that I would like to address this afternoon: when and how to approach circuit designers without telling them the secrets, for example; when to cross the bridge, whether to look for venture capital money now or to wait 1 year until we demonstrate the advantage. These trivial questions. And another trivial question, whether it is worthwhile joining forces with with the big semiconductor companies or doing something different. So I would like very much, again, to thank you for coming here, and I'll appreciate very much to discuss these issues this afternoon. Thank you very much.
This program was brought to you by Koller Institute of Venture at Tel Aviv University.